this video, we're going to take a look at converting between polar and rectangular form equations. The last video, we saw what a polar form is and how those points work. But of course, whenever we're graphing anything, we don't just deal with individual points. We also deal with entire equations. Equations just being connecting multiple points, or really an infinite number of points. So that's what we're going to concentrate on in this video. We're going to use the same formulas, the same key equations that we used when we were working with polar and rectangular points. And really, these four formulas we've seen over and over again in trig. Sine, cosine, and tangent. We've used these over and over again, and then the r squared, this is just the Pythagorean theorem, we've used this as well. So these are the four basic equations we keep coming back to. Now, one thing I say over and over again in this class is that it always helps to start to draw a picture. This is going to be one of the few exceptions to that, because we haven't gone over what the polar form equations look like yet. So we are going to approach these more from the algebraic side, not be able to have that picture in our mind. And that's fine. We'll get there. We're going to see those eventually. Now, what I do want to point out is that these are equations, which means we can solve for any piece that we would like. So really, it's going to be very helpful in these first two equations to solve for the y and the x. So y we can get by multiplying that r over to the other side. Y would be equal to r sine theta. The x would be equal to r cosine theta. Of course, we could do this for any variable, but these are going to be the two that really are very helpful to solve for, and we're going to see how these all play in. Now, if we remember when we're solving, or when we're converting between rectangular and polar points, we said it's much easier to convert a polar to a rectangular. We kind of went in that direction first. And the equations, I'm going to convert from rectangular to polar first. So we're going to take several examples in this video. Let's convert from rectangular to polar form first. And the reason that this direction is much easier is we're only going to concentrate on two formulas, those being the two that we just found. If we want to go from rectangular to polar form, what that means is that all the rectangular variables, the x and the y, need to be gone. We shouldn't see any x and y left, and we want only r's and thetas being those of the polar form. So let's start off with just a very basic example. Let's take y is equal to 3x plus 2, just a nice linear equation. I want to put this into polar form. So what we just said is that y is equal to r sine theta, x is equal to r cosine theta, and notice I'm already basically there. We have only r's and thetas, we don't have any x's and y's, and that's the key. Now I'm going to go a step further, because just like we do when we put things in rectangular form, we typically want to solve for the y. Now when we're putting equations into polar form, we're going to solve for the r. So let me just add that in the instructions here. Solve for r, and then occasionally we'll have to solve for r squared, but we'll see examples down the road of some different looks these things might take. So if I want to solve this for r, I want to get the r's to the same side, meaning I'm just going to subtract that 3r cosine over to the left side. Once I have both of those r terms on the left side with no other non-r terms over there, I'm going to factor off the r. And I write that as a sine, and that, of course, should be a cosine. 3 cosine. And that's equal to the 2. And now if I want to get r all by itself, I'm just going to take all the stuff that's not r and divide it over to the other side. And so there's my equation for r. Now, like I said, we can't get the graphical image in our head. No, we do know y equals 3x plus 2 looks like that's a line. This is also a line. If we were to, when we figure out how to graph these things, this will also be a line. We just don't recognize it as such yet, and that's the reason we can't get that graphical image in our head. Let's move on to a second example, and this one's going to be a little bit more complex. Let's take the equation x minus 3 squared plus y squared equals 9. And I should recognize this. This is an equation of a circle. It's the x squared plus y squared equals the radius squared. So we know the center of the circle would be 3, 0, and the radius would be 3 as well. So we do know what this looks like in rectangular form, but again, we don't know what a circle looks like in polar form, because this polar form is brand new to us. I'm going to treat it the same way I did the last problem. That's why I say that going from rectangular to polar is much easier. It's very formulaic. Every single time, we can just take that x and we can replace r cosine theta, because that's what x is equal to. Every single time. And y is r sine theta. every single time. Very formulaic. Now, where we go from there is a little bit different. Depending on the algebra that we need to solve, we just need to solve the problem. So again, our goal is to get that r by itself. But right now these r's are a little bit tied up. So we need to get them out of the squares, and we do that just simply by squaring. So we square this first term, we'd have r squared cosine squared minus 6r cosine theta plus 9. And this is just squaring a binomial, so we square the first term, the r cosine, we multiply the 2, and then double it, negative 6r, and then we square the last term, that's where we get the 9 from. And then we want to add to that the r squared sine squared, that's equal to a 9. So this is looking more complex than the last example, but it's really after the same thing. We're doing the same thing. We're trying to isolate that r. And so I'm going to go ahead and get these r squared terms side by side. And hopefully the reason for that is pretty obvious, but we'll talk through if not. So we are trying to get the r terms together, but right now there's too many r terms, right? We can't just factor out the r because it's not set equal to 0 yet. We can set it equal to 0 pretty easily. And then as it stands, we can't factor this down any, so we're kind of stuck. But when I put these r squared terms next to each other, what I notice is I can factor the r squared off of the cosine squared plus sine squared. Need the theta in there. And we know that cosine squared plus sine squared is just a Pythagorean identity. That is just equal to 1. So this is just really r squared times 1, which is r squared. 6r cosine. And then I do want to get this thing set equal to 0, so I spring the 9 over, they happen to cancel out. We are left with the equation r squared minus 6r cosine theta is equal to 0. Now that I have it set equal to 0, I can factor off that r the same way we did the last example. So we're left with the equation r times r minus 6 cosine theta equals 0. And so typically when we factor, we set both of the factors equal to 0. So I'll do that for just a second and we'll talk about it. So the first one, r equals 0. The second one, r would be equal to 6 cosine theta. And this is what I would get. Now I really only want one equation because that first one was really only one equation. So which equation do I choose? I only need to use this equation right here. The r equals 0 is a redundant solution. We know that cosine takes on a value of 0, right? And we're not restricting these thetas or r's in any way. It's just the same way we didn't restrict x and y in the original equation. It's just whatever values they take on. So theta can give us a 0 for this cosine. And so r equals 0 is already included in the solution, which is why this one equation solves, is the full equation. That is our final answer, the 6 cosine theta. So again, the same process there. We replace the x's with r cosines, the y's with r sines. We do the algebra to get the r's by themselves, and then once we do that, we have our equation. Pretty straightforward. What does tend to be the more challenging direction is going from polar to rectangular. So let's go the other way. Let's convert from polar to rectangular form. And the reason this is more challenging is because it's not the same thing every single time. The ways that these will be presented are going to look, they're going to be presented in a number of ways. There's a variety of ways these things could look. And so we've got to think about these 4 formulas. We've got to choose which one is going to be most useful to us. So let me just copy these down to the bottom of my screen real quick so I have them sitting right there. Because we are going to have to constantly make this decision, which formula do I need to be using? Let's take this example for starters. Let's take the example r is equal to 6. Very simple equation. This is a polar form equation. We know that because it has just an r. Well, it could have a theta as well, but in this case it doesn't. We want to go to rectangular. So when we're going from rectangular to polar, we're thinking we want to get rid of x's and y's. We want only r's and thetas. Now we're doing the exact opposite. We want the x's and y's. We want to get rid of the r's and thetas. So the r needs to go away. We think about the formulas we have available to us. Remember the sine, we said that we can write this as y equals r sine theta, x r cosine theta. We could solve for x or y in the tangent, and we have the r squared equals x squared plus y squared. If I think about which one's useful to me, we see r's in 3 of the 4. So tangent's definitely out. That one, without a question, is not at all useful to me. The sine and the cosine have r's, but they also have a theta. I don't have any thetas in this equation, and to bring them in would be kind of a pain. So for instance, I could multiply this by sine, and we know that our sine theta, we can write that as a y. So if I chose to, I could multiply sine right here, meaning I'd have to do on this side as well. And sure, then sine r is just y, and so we're closer. But notice, what have I done then? I've introduced a sine on the right-hand side, and we have another problem now. We have another theta we have to get rid of. So I don't want to create a variable that's not there. If I don't have a theta, let's not go adding more thetas. If I don't have an r, we won't add r's. So I'm going to concentrate on this last formula right here. R squared equals x squared plus y squared. That only has r's in it. That's perfect. That's what I want. Problem is, it's an r squared, not just an r. But we can always do both things to both sides of the equation without changing it. So why don't I square both sides of this equation? I square this left-hand side, I square the right-hand side. So now I have r squared is equal to 36. And r squared, I know exactly what that is. That's x squared plus y squared. Notice I have an equation now that only has x's and y's. There are no r's or thetas. So we're done. We have actually found out that this equation right here is in fact a circle, r equals 6. Now that step of kind of multiplying in the r might seem a little bit foreign, not multiplying an r, but squaring the r. Remember, we just got rid of an r a second ago, so obviously when those r's are equal to 0, meaning it's a factor of r, they're not real important. Or here we've squared, so what we're saying is it doesn't matter if r is positive or negative, and we've seen that in the past, right? When we were plotting points, we said if r is 6, that means we go out 6 circles, right? 1, 2, 3, 4, 5, 6, wherever it ends up. We can go out any which way from that point. So let me just clean this up real quick and say that this is our r equals 6 circle. Because the angle is not specified, it's saying we could go here, we could go here, we could go here, we could go here. So if I'm going here and here, notice I've just traveled a negative r. And so that's why having a positive and negative r's don't matter. So again, that's a little bit technical. That's kind of the idea behind it. But the step there was recognizing, well, I only have an r variable. I want to just use that r variable, and that means I need to use that fourth equation. Let's take another example. Let's squeeze this one side by side so I can refer to those key equations again. Let's say this time we have theta is equal to 45 degrees. I need to convert this to rectangular form. Well, I go kind of through the same process of elimination. These top three have thetas, the last one does not, so this one's not at all useful to me. But I don't have an r, so the same way before we said we don't want to create that theta, I don't want to suddenly create an r. So I'm going to rely on this third equation right here. But if I'm going to rely on this third equation, I need a tangent in front of that theta. Well, great. Let's put it there. If I put it in front of the left-hand side, I also have to put it in front of the right-hand side. I have to do the same thing to both sides of the equation. And so we're going to have tangent theta is equal to tangent of 45. We know exactly what that is. That is just 1. And tangent of theta, if we were to write in rectangular form, is simply y over x. And solving for y, because that's what we do when an equation is in rectangular form. Get my pen working here. Y is equal to x. Notice the last one I didn't solve for y because that was a circle. So when we're converting to rectangular form, we generally either want to be solving for y or we want to put equations into the standard form of the circle. That's going to be kind of our two goals. So here we chose a completely different formula than we did on the first one, but the idea was the same. We're referring to these four formulas and we're saying which one is the most useful to me. I have a theta, I'm going to have to choose one of the top three, but I don't want to bring an r into it, so I'm going to use that third formula right there. Let's move on. Let's take the example. R sine theta is equal to 5. So, well, let me copy my formulas back down here so I have them sitting right next to the problem. R sine. Remember we said that these top two equations we can rewrite as r times sine theta is equal to y, and r cosine theta is equal to x. So clearly here I right away have y. There's no work that really needs to be done. Y is equal to 5 is my answer, just through that direct substitution. So this one, we have the r and the theta, so we're probably going to refer to one of the ones that had the r and the theta, the top two, and because it has a sine in it, I'm obviously going to choose one with sine. That one was pretty straightforward. Let's take r equals 3 secant theta. All right, well now we got a problem because I don't have any secants in my list. I have sines, cosines, tangents, no secants. I see that I have an r and a theta, but really I'm not concerned about that for right now. What I want to do is I want to get rid of that secant theta. And I know that I can write secants as 1 over cosine. So let's start there. That's looking better. I feel more comfortable with that because I've gotten rid of secant and I have cosine that is in my list of equations. But I don't know how to treat a cosine in the denominator. I really need these variables to be in the numerator. And so let's just take that cosine and multiply it over to the other side. R cosine theta is equal to 3. Well, by starting with something I was uncomfortable with and rearranging it to things I was more comfortable with, I knew I wanted cosines. I knew I wanted things out of the denominator. I've gotten r cosine, and that is exactly what we know x is. And so again, once we get to this point, it's just that direct replacement. X is equal to. Very straightforward. Let's take the equation. R is equal to 4 sine theta. All right, well, here we have the sine and the r split, and it's not like the last example where that sine is in the denominator to where I can multiply it back over and suddenly works out. If I were to move the sine over, it would be r over sine theta, which is not equal to y. That's not any of my formulas. I want to keep those equations and those variables out of the denominator. What I know I need with that sine is an r. Now on this left hand side, the r is a problem too because we need it to be an r squared or an r sine, r cosine, so forth. But we're going to use kind of the same idea that we did in that first example where if I have an r sitting here, I don't want to just bring in another sine or cosine. But we did say both sides need another r. So why don't I just multiply both sides by r? Again, I'm not changing the equation. I'm doing both sides, the same thing to both sides of the equation. And like that last rectangular to polar form we saw, r equals 0 is always a legitimate factor. It's always a solution because we knew this equation contained 0 to begin with. And so once I multiply that r to both sides, I get r squared is equal to 4r sine theta. R squared is equal to x squared plus y squared. And r sine is equal to a y. And so now we've converted this thing to rectangular form. Notice we have only x's and y's. We have no more r's and thetas. Now this is a circle, which means I do want to put it back into the standard form of a circle. So I'm going to move my 4y back to the left-hand side. I have to complete the square, so I'm going to leave myself a blank. I'm going to look at that form and I say, well, what is half of negative 4? It's negative 2. I square it, which is of course 4. So we'll have x squared plus y minus 2 squared is equal to 4. And there is the standard form of my circle. Now getting to this part right here, let me put it in blue. Getting to this part right here and then going here, those are the two new steps. So really at the end of my blue line right there, that's the new stuff. Under that blue line, if I kind of lost you there on completing the square, go back and rewatch a completing the square video, or I have a video on circles too I can refer you to. But we want to make sure that we are comfortable with converting from a general form or any non-standard form equation to a standard form for circles. We're going to see that even more in the next chapter. So that is an important skill. The top half here is the new stuff. The bottom should be old hat. Let's take another example. So I think I'm up to 6. Let's take r equals 3 cosine theta plus 2 sine theta. Well, very, very similar to the last one. I have thetas and r's. I know I need the r's with the cosine and the sine. And I know on this r right here that that needs another r. So simplest thing to me is just to multiply everything by r because everything needs an r. I don't want to try and square this side because then I have some cosine squareds and sine squareds still lacking r's. So when we're thinking about these, the recommendations I would always make is think about the pieces you have, obviously look at that, but think about what's helping everything at the same time. That is preferable. Now sometimes we might just need to work with the form to get into a more comfortable form. That's always got to be the first step. We want to see the sines, the cosines, and the r's, everything out of the denominator. Start there. But then once we have that, we're looking at what makes everything work. Is there a way I can make everything work at once? If we do something to just 1/2 of it, I always recommend don't convert until you have a strategy for everything. That's a good general rule. So for instance, if I were to have squared this in my first step, I'd have r squared equals 9 cosine squared plus 6 sine cosine, and then 4 sine squared. So I'm just kind of scribbling this in because it's not going to look pretty at all. Don't convert this to the x squared plus y squared because you have no strategy for the right-hand side. The cosine squared is not going to be an easy fix. The sine cosine is not going to be an easy fix. The sine squared is not going to be an easy fix. So before you get converting, really think about how is everything going to work out in this problem. It's a lot easier than just trying to convert part of it. So if we multiply by the r, we get r squared is equal to 3r cosine theta plus 2r sine theta. And so once again, we see that everything's working out pretty cleanly. X squared plus y squared equals 3x plus 2y. And we do have another circle that we need to put into standard form. So I'm going to get the x terms together, subtract the 3x over. I'm going to leave myself a blank to complete the square. I get my y terms together. I'm going to leave myself a blank there to complete my square. That means I'm going to have 2 blanks being added together on the right-hand side. For the x's, I look at half of 3 is -3/2. Square it, it's 9/4. Put it on the other side to keep the equation balanced. Half of -2 is -1. Square that. That's going to be a 1. Keep the equation balanced. So I have x minus 3/2 squared plus y minus 1 squared equals 9/4 plus 1 would be 13/4. And there's my equation. Let's take a look at one last example. In this one, I'm going to take r squared sine 2 theta is equal to 6. So we look at this and we say, well, r sine theta is equal to y. So maybe I'm thinking for half a second I have an extra r hanging out here, but that's not true actually, because we don't have a sine theta here. We have a sine of 2 theta. And sine of 2 theta is not the same as sine of just theta. So I need to start here by getting just thetas. We can incorporate any of the trigonometric formulas we've been learning in the last few weeks into these problems as well. So if we think about the sum and difference, the half angles, double angles, any of those we can incorporate. But we need these things just to be thetas. So recall that the double angle formula tells me sine of 2 theta is equal to 2 sine theta cosine theta. And now we have sine and cosine just with the angles theta. We have this r squared out front, and that's perfect because what we're thinking here is this sine needs an r, this cosine needs an r. This is all multiplication, so we don't want to distribute. I don't want to say this is 2r sine squared, 2 sine, r squared sine squared, r squared cosine squared. I'm not going to distribute. This is all just multiplication. So this r I can really think about as r times r. It's the same thing. I'm going to take one of those r's and stick it with the sine. I stick the other one with the cosine. And r sine is y, r cosine is x. And now I just need to get the y by itself, and I do that by dividing over. So we get 3 over x, and there's my equation. That's it. So in the next unit, we're going to see how to graph these trigonometric formulas when they're in polar form, how to graph these equations when they're in polar form. Right now we're just working on this conversion, and that helps a lot because if we can convert from polar to rectangular, we already know what it's going to look like, so we have a pretty good idea what it should turn out to be. But it is important to be able to work with both of these forms. We talked about that with just the points. We saw how the points can be valuable in polar or rectangular form. We're using those same 4 equations, these same 4 equations we've used chapter and chapter again, right? And we're going to continue to use them. We're going to use them a ton. Sine theta is equal to y over r, cosine theta is equal to x over r, tangent theta is equal to y over x, r squared equals x squared plus y squared. Same 4 basic formulas we learned the first week of class, we're just applying them in new ways.